So for our second exercise, let us remind ourselves that it is recommended that you pause the video once the problem statement has been formulated, and then try to solve the problem yourself before moving on to watch the solution in the video. With that being said, the exercise in front of us is to compute the Christoffel symbols in polar coordinates. And to remind ourselves of the results from the last exercise, the tangent vector basis in polar coordinates is given by E rho equal to E1 cosine phi plus E2 sine phi, and E phi is rho times minus sine phi E1 plus cosine phi E2. In order to compute the Christoffel symbols, we need to compute the partial derivatives with respect to the coordinates of the tangent vector basis vectors. We start by computing the derivative in the rho direction of E rho, and since E rho does not depend on rho, this partial derivative is equal to 0. According to the definition of the Christoffel symbols, this should also be equal to gamma rho rho A times EA, which if we write out the sum over A is gamma rho 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 times E rho plus gamma rho rho phi times E phi. Identifying this with a 0, this means that both the Christoffel symbols gamma rho 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 and gamma rho rho phi are equal to 0. Taking the derivative of E rho in the phi direction, we find that this is minus E1 sine phi plus E2 cosine phi, which if we compare with the tangent vector basis, is equal to 1 over rho times E phi. But it should also be equal to gamma phi rho A times EA, which is equal to gamma phi rho rho times E rho plus gamma phi rho phi times E phi, and identifying this with the result we got from the differentiation, we find that gamma phi rho phi is equal to 1 over rho and gamma phi rho rho is equal to 0. We repeat the process for E phi and find that the derivative in the rho direction is minus E1 sine phi plus E2 cosine phi, which is 1 over rho times E phi. This again gives us that gamma rho phi phi is 1 over rho and gamma rho phi rho is equal to 0. For the derivative in the phi direction, we obtain minus rho times E1 cosine phi plus E2 sine phi, which is equal to minus rho times E rho. From this, we find that gamma phi phi rho is equal to minus rho and gamma phi 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 is equal to 0. And we can mark up the answer to this exercise as the resulting Christoffel symbols, 5 of which are 0 and 3 of which are non-zero. It should be noted that we have here found that gamma phi rho phi is equal to gamma rho phi phi. This is not a coincidence, but rather a direct result from the definitions. Since EA is equal to the partial derivative in the A direction of the position vector, this means that if we take the derivative in the B direction of this vector, we find that this is dB, dA acting on x. Exchanging the order of the partial derivatives, we find that this is dA, dB acting on x, which is equal to dA acting on EB. This means that gamma ABC must be equal to gamma BA. Looking at the graphical interpretation of our results, we can draw the tangent vector basis as in the previous exercise, and if we follow this line, it is a coordinate line of the coordinate rho. And we can see that along this direction there is no change in the tangent vector E rho, which is compatible to us finding that gamma rho 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 and gamma rho rho phi are equal to 0. On the other hand, the tangent vector E phi does change, and that its length grows with the coordinate rho, as indicated by its partial derivative with respect to rho being proportional to itself.